Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about another very important topic, and that is the orthogonality of eigenmodes. Let's jump right in. In the last two videos, we already talked about how to get the eigenmodes and we did also an example, so you better understand how to work with it. Now we can look at how those eigenmodes are orthogonal to each other, and we will need that to solve big systems later on. So let's look at our equation that we had from before. We had our system with our eigenfrequency and our eigenmodes, and this is of course equal to 0 and x is not 0. So what if we pre-multiply this equations that we had right here with x? So we first multiply it. We had this one. We went from here to here. We remove the parentheses, and we pre-multiplied it with s. Now, if we have the same equation, but this time with not omega r, but omega s, so a different omega, we have this equation where we have xs, omega s, and xs, and we pre-multiply it with the opposite, so xr. So we pre-multiplied this one with xs because we had xr's. Here we have xs's, and we pre-multiply with xr. So we got, let me remove this one. Now we have this term, and we have this term. So we kind of did the same thing twice. But this is very important, because if we now subtract one term from the other term, we will get this equals to that. So we have our xskxr minus xrkxs, and because this is basically a minus a, we will get a 0. So these two terms are the same, but not for these two terms. We have this one and this one, but we have a omega r here and a omega s there. So we can't just say that this is basically b minus c and this is not 0, because we have different eigenfrequencies involved. So we are left with this term. And because this term must be 0, and these two eigenfrequencies are definitely not the same, I forgot a square here, these two eigenfrequencies are definitely not the same. The only thing that can be 0 is this part. So this one must be 0. So xs transposed m xr is 0, because those eigenmodes are m orthogonal. Xs transposed xr is not equal to 0, so they're not orthogonal in a geometric space, but they are orthogonal when we pre and post multiply them on M. So we call that M orthogonality. And if we know that, we can look at for example, this equation right here. We know that this must be 0, because this is 0. This is irrelevant now. We already see that this is also, so we define this as also to be 0. So we have K orthogonality. If we pre-multiply xr to ksxs, we will get 0. So what does that actually mean? It means that the work produced by inertia forces, the inertia forces is this part, the inertia forces on mode r, this is mode r, the work is 0. And the work produced by elastic forces, that's the k, where is it? Here, for example, k, of mode r projected on mode s is 0. So we had elastic forces of mode r projected onto s is 0. That's what K and M orthogonality means. So we can do that. Of course, we have also the quadratic form, and we have a xr transposed k xr, and we call that a gamma r. And if we have xr transposed m xr, we call it mu r, and this is basically our modal stiffness and modal mass. Notice that we have twice an r here, so it's not 0, but it's the modal mass. And when we have those modal masses and modal stiffnesses, we can get the eigenfrequency, and this is called the Rayleigh quotient. So as xr can be chosen freely, that's where we can define one value and get the other one from the videos before, we can choose xr, or x in general, in such a way that if we pre and post multiply it, we get a 0. So we can have a new definition, or not definition, but a new way of writing it, that if we have a pre-multiplication and a post-multiplication of two different values, they will be the eigenfrequency only if r and s are the same. And if we have a pre and post multiplication on the M matrix, on the mass matrix, this will be unity, because this is a Kronecker delta that is 1 if r is equal to s. So let's look at an example. This might be very difficult to understand, but I'll do my best to show it with an example. So we had the double pendulum from the last video. Now we had one eigenshape and the other eigenshape. We had the stiffness matrix and the mass matrix. Now we get the modal mass by pre-multiplying with the first modal mass by pre and post multiplying the first eigenshapes, and for the second modal mass, the second pre and post multiplication of mass n of the second eigenshape. So we get two eigenmodes, and we do the same for the stiffness, and we get two modal stiffnesses. Now, if we want to check, did we do the right thing? We can look, we can divide one by the other. So gamma 1 by mu1 and gamma 2 by mu2. And we get the exact same eigenfrequencies that we had from the video before. So we're on the right path. So if we want to do the mass normalization that I mentioned right here, we have to set this to 1. So we have a 1 here. That means we have to divide this part by mu. But we can't just divide by mu, because we have to change each eigenshape. So we divide each eigenshape by the root of mu. So now we have a new eigenshape that we can change to get a modal mass of 1. So for example, if we had this as our original eigenshape, we divide it by the square root of our first, that's very important, where it is, there it is, our first modal mass, and we get a new eigenshape. The shape is completely irrelevant because the ratio is still the same. The ratio is the only important thing. The values itself, they are only important for the mass normalization. Where is it? Where did I put it? There we go, the mass normalization. So mu1 will be equal to 1 if we pre and post multiply with our new adapted eigenshape. I hope this video gave you a small understanding on how we can work with those orthogonality of eigenmodes and understand better what's actually going on. I'll try to summarize it real quick. We proved with the help of pre-multiplication and post-multiplication that our eigenshapes are M orthogonal, and if they are M orthogonal, they are also K orthogonal. And that means that the inertia of mode R on mode S is 0, and the elastic forces of mode R projected on S are 0. Then we defined the modal mass and the modal stiffness and modal mass, and we said that we can set the modal mass to unity if we divide it by, there we go, if we divide the eigenshape with the square root of our modal mass. And this is basically all there is to it, to the orthogonality of eigenmodes. We will be working with this topic many times over. So if you don't understand, feel free to ask comments in the questions down below. I will do my best to explain everything. Thank you very much for your attention, and I'll see you next time.